This is lecture 1.6, which is all about how you do stoichiometry when you're dealing with solutions. So, as usual, please make sure you've created your own learning target notes in your notebook first, and then come back and start adding the examples and other information from the lecture. Stop the video if you need to, and then restart it when you're ready. Okay, we can move on. So a few things that you need to remember from stoichiometry is that you always have to have a balanced equation. Either a molecular or a net ionic equation will work. When we're doing solutions, often we use net ionic equations because most of our solution reactions have net ionic equations that are different from the molecular equations. Make sure that if you're using a net ionic equation, you're remembering to find the concentration of the ion or the moles of the ion in solution, not using the whole compound. So you have to be really careful with that. And remember that we might have limiting reactants, and the way that you'll know that is that you're given amounts of both reactants. We're using a lot of solution stoichiometry. We use molarity all the time because the way that you get from volume of a solution to moles of the solute is molarity as your conversion. So the volume of the solution will be in liters and the moles of solute will be what you're looking for, or back and forth. The process is pretty much always the same as it has been, and if you don't know what you're looking for, then you work backwards from what you asked to find so that you know what you need to solve for in your stoichiometry. So let's do a couple of examples. Stop the video so that you can copy the question if you need to, and then restart it when you're ready. Okay, so this one is not a limiting reactant question. This is just a solution stoichiometry question, and it's actually a combination of a solution and something that's a solid. So the first thing that I need to think about here is that they've given me an equation, but they said it was unbalanced. And then I'm going to react 2.15 kilograms of UO2, and they want to know how many liters of 0.24 molar hydrofluoric acid would react with that. So the first thing I need to do is balance my equation so that I can use that in my stoichiometry. This is a pretty easy one to balance. I need, let's see, I need 4 HFs to take care of the 4 fluorines, and then that means I need 2 waters, and then everything else should balance. So we're going to do this the same way we've always done stoichiometry. We're going to start with our given, 2.15 kilograms, and this is a solid. So this part's not solution stoichiometry. This is just like what you've done before of UO2. My first step is going to be to get my given to moles, so I have to go from kilograms to grams, and it's the same substance, UO2. And then remember that 1 kilogram is 1,000 grams. And then I need to go from grams of UO2 to moles of UO2. This is also nothing new for you. I'm going to use the molar masses off the periodic table. I use 238 for uranium. So 1 mole is 13.3. Sorry, 1 mole, wow, that was weird, is 270 grams of UO2. And now comes the step that really makes it stoichiometry. I have to get from UO2 to HF. This has to be in moles, moles of UO2 to moles of HF. And from my equation, this is 4 moles of HF for every 1 mole of UO2. And now finally, new step right here, solution stoichiometry. We need to find volume of the HF solution. Remember, this is liters of solution, and the HF is the pure substance in the solution. So right now, what I have here is the pure substance, moles of HF, and I need liters of solution. Remember that molarity is moles of solute in liters of solution. So when it says 2.40 molar, this means 2.40 moles of HF equals 1 liter of solution. So that's going to come in here as my new conversion factor, and I'm going to be finished. So I'll give you an answer so that you know it. I got 13.2716, and with 3 significant figures, I think, from both the molarity and the mass given, it's going to be 13.3 liters of HF solution. Okay, so this is just to get you used to using molarity as a conversion factor. We don't often do mixed reactions like this where you have a solid and a solution, but every once in a while, so I wanted to show you what that looked like. Okay, now comes the fun part. This is all about limiting reactants. So in this one, your book does not just deal with limiting reactants of precipitation reactions, and this is where you will need these steps. So if you need to stop the video for a second so that you can copy the steps, then copy the steps and restart the video. All right. So the hard part about this is that not only are you going to be asked often to find out how much precipitate is formed, maybe they won't even ask you that. What they are going to ask you to find, and what is relevant to us, is what's left in solution when we're finished. So you have to remember that if you're given volumes of two different solutions that you know the molarities of, then technically you know the number of moles of each ion, and now you have limiting reactant situation. The easiest way to do these is actually in kind of baby steps. And I'm going to show you how you're going to figure all this out, but you're going to decide which ion is limiting reactant, and then remember that because it's the limiting reactant, it will be all gone when the reaction is finished, and its final concentration will be 0 molar. You also need to decide which ions are spectators, because the spectators don't get used. So the same number of moles that were present in the beginning will be present at the end. But the biggest difference is that you've usually poured two solutions together, so those moles are swimming in a bigger volume. Okay, and then finally, the hard one is the limiting reactant and how much is is the excess reactant and how much is left over. So this is the one where you have to do that step of figure out how much you use in order to use all of your limiting reactant and subtract it from how much you started with, and that has to all be in moles, and then divide by the new final volume. So in a way, you kind of need to have the conceptual idea of what's going on here before you can go any further. So we're going to do an example, and I want you to think conceptually first. What I have is a beaker with 10 milliliters of 0.3 molar sodium phosphate solution, which means sodium phosphate is Na3PO4, which means that what I really have is Na pluses and a PO4 3 minus. And those are going to be in a ratio of 3 to 1, and the total concentration is 0.30 molar. Molar. So there's 0.3 moles of phosphate, but 3 times that many moles of sodium ions. And I have another beaker that contains 20 milliliters of 0.2 molar lead 2 nitrate. So lead 2 nitrate is PbNO3 twice, which means that I have a Pb2 plus and 2 NO3 minuses floating around in there for every mole, right, or for every one. So really what I have is 0.2 molar Pb2 plus and 0.4 molar nitrate. If that's confusing to you, I'll show you those calculations in just a second. What's going to happen is I'm going to pour them together. So I pour one into the other, and the decision has to be who's going to precipitate. In this case, sodium and nitrate are always soluble. So what happens at the end is that I have a beaker that now has 30 milliliters of liquid, 30 milliliters of solution. There's some lead phosphate, Pb3PO4 twice, sitting in solid on the bottom. And then in the rest of this volume up here, there's going to be the spectator, which would be the Na pluses and the NO3 2 minus, or the NO3 minuses, and whoever's not limiting, plus my excess ion, however much is left over. Okay, this is a really big conceptual thing, that this is going to react until the ion that's limiting runs out, not going to react until the whole compound runs out. And remember that your spectators will all still be present, they're just swimming in a bigger solution. So their molarity will change, but the number of moles does not change. All right, so the easiest way to do this before you begin is to find moles of everybody. So this means that I have 4 ions. I have sodium ions, I have phosphate ions, I have lead 2 ions, and I have nitrate ions. And I want to find moles of each. All right, so I have to do this from the volume and the molarity. I'm going to start with the volume. The first one I'm going to show you the long way. There's 10 milliliters of solution with sodium phosphate in it. And in order to use molarity, I have to convert milliliters to liters. Then I'm going to use the molarity to get to moles of Na3PO4. And then I'm going to get to, from moles of Na3PO4, to moles of sodium ions. All right. So this conversion, 1 liter, 1,000 milliliters, you can do in your head if you'd rather. I'll show you that for the next one. And then this conversion is your molarity. Okay, so in this case, it's 1 liter of solution would have 0.30 molar sodium phosphate. And then for every sodium phosphate, we, when it dissolves, because of the subscript, get 3 sodium ions. And this is, whoops, it's not going to show up there. This is from the subscripts. Okay, so I can solve this and find that I'm starting with 0.00900 moles of sodium ions. Okay, I can do the same thing from the phosphate. I don't have to do the 10 milliliters to 1,000 or to liters there. I can move my decimal 3 to the left, which would be 0.0100 liters of solution. And you want to remember these are solution, right? So this will be liters of solution to moles of, again, sodium phosphate. And this would be 1 liter and 0.3 molar from the molarity. And then for every 1 mole of sodium phosphate, in there is 1 mole of phosphate ions. So when I do that, I get 0.030 moles of phosphate ions. So I want you to stop the video and try this for the lead and the nitrate using the given molarity of 0.2 molar lead nitrate and 20 milliliters. And take a second to copy the example if you didn't already stop the video to do that. Okay, so I'm going to do this for you and walk you through it. Point for the lead 2, this is going to be 0.0200 liters. In 1 liter of solution, there was 0.2 moles of lead 2 nitrate. And in 1 mole of lead 2 nitrate, there are 2 moles of lead 2 ions. And that gives me 0.00400 moles of lead 2 ions. I can do the same thing for the nitrate. It's going to look the same at the beginning. For every liter, there's 0.2 molar. But for every 1 mole of lead 2 nitrate, there's, oh, I messed this up. Sorry, hang on. Whoa, did not mean to do that. You come back up here. Sorry. Fix this in your work, right? From lead 2, in lead 2 nitrate, there's 1 mole of lead and 2 moles of nitrate ions. Okay, so my answer was correct because I took it off of my answer key that I made, but my work was incorrect. So please make sure that you fix that. For every 1 mole of lead 2 nitrate, there is 1 mole of lead 2. Okay, and for nitrate, for every 1 mole of lead 2 nitrate, there are 2 moles of nitrate. And that gives me 0.00800 moles of nitrate ions. And now you might be asking yourself, why do I care? So when I mix all 4 of these ions together, who is my precipitate? This is what you have to ask yourself. So the precipitate that I see would be lead 2 phosphate. So this is going to be PB3, PB3 PO4 twice. Okay, this is my precipitate. So I need to write my net ionic equation to form lead 2 phosphate. And that means that I need lead 2 ions and I need phosphate ions. And this would be 3 lead 2 ions and 2 phosphate ions from the subscripts. Those become the coefficients on my ions. all right? This means that I can come back at this list and look right away and identify the sodium as a spectator and the nitrate as a spectator, because they're not going to be part of the precipitate. So if I want the molarity of the spectators when I'm finished, those moles don't change, but the volume does. I can do these first if I want and get them out of the way, or I can do them at the end. I'm going to go ahead and do them now so that you can see this process. Remember that the spectators are not reacted. So moles at the end equals moles that you started with. They're just floating around in a bigger beaker. And the volume went from smaller volumes, either 0.2 liter, either 20 milliliters or 10 milliliters, to a total of 20 milliliters plus 10 milliliters, right? Which equals 30 milliliters, which really equals, you have to be in liters to do molarity, 0.0300. Oh, it was 20.0, sorry, 10.0, 0.0300 liters of new volume for my solution, okay, my total volume. So if I want the molarity of the sodium ion didn't change in moles. I had 0.0900 moles of sodium ions. So this is going to be 0.0900009, sorry, 00 moles of sodium ions in this new volume, which will be 0.0300 liters. And that gives me a molarity of 0.3 molar. And I have 3 significant figures, so I'm going to make it 0.300 molar sodium ions. All right. You stop the video now and see if you can do the molarity of the other spectator, which is the nitrate. Okay, so to do the nitrate, the molarity of the other spectator, I'm going to do the moles that were there, which are 0.00800 moles, because they didn't react, they're just floating around. And my new volume, 0.0300 liters, gives me a final molarity of 0.26666, a bunch of numbers. So I'm going to round that to 3 sig figs at 0.267 molar nitrate. So that's how you find the spectators. Now I want to find the limiting reactant so I can figure out who completely runs out, and I need to figure out how much excess is left. So to find the limiting reactant, you can do this one of 2 ways. You can go from the moles of one of the phosphate so the 2 that react are the phosphate and the lead. You can start with one of them and go to the product, or you can start with one of them and go to the other reactant. Since this question asks you for how much precipitate is formed, you might as well go to the product. So when I did this, I started with, I started with both, okay. So I started with, change color so you can find my new stuff. To find the limiting reactant, I'm going to start with my 0.00300 moles of phosphate ions and my who's my other reactant? Lead, 0.00400 moles of lead 2 ions. And I'm going to figure out how many moles of, or even grams if I want to, of precipitate would form. This is my product, right? So moles of phosphate or moles of lead ions, 2 moles of Pb3, PO4 twice, Pb3, Pb3, PO4 twice. And from my equation, I can see that for there's 1 mole of the product formed for 3 moles of lead and 2 moles of phosphate. So I'm going to say 1 mole of the product formed for 3 moles of lead and 2 moles of phosphate. And if I know that I'm going to grams, it didn't ask in this question, but often it will. I'm just going to go ahead and go on to grams now because I'm going to go ahead and answer that question. So I will go from 1 mole of Pb3, PO4 twice to grams of Pb3, PO4 twice. And I looked up the molar mass to find it as, I'm looking, 811.54. 811 actually I didn't do this till after I figured out limiting reactant, so I don't know my numbers, but 811.54 grams of that product. I actually want to show you that it's way faster to not do this step until you know who's limiting, because it's faster not to do all that math. So 0.003 divided by 2 is 0.0015 moles of product that would be produced. And 0.004 divided by 3 is 0.001333 repeating moles of PB3PO4 twice that would be produced. So in all limiting reactant calculations, the smaller one is your theoretical and the other one is impossible. And now if I need to, I can go on to grams. I don't really care, they didn't ask me, but I could take that and go on to grams. Or if I'm going to leave it in moles, then I would make it 0.00133. I have 3 significant figures, moles of lead phosphate produced, right? So that answers that question. And it also tells me who's limiting reactant. So remember that the one that's smaller, the one that produces less product is the one that runs out. So that means that this is my limiting reactant, which would be my lead ions. And that means my excess reactant is my phosphate ions. Okay, so my lead ions, the molarity of the lead is 0. And this is because it's the limiting reactant and it's going to run out. So now I have only the excess left. And in order to find excess of PO4 3-, I need to know the PO4 3- I started with. And I need to subtract the PO4 3- that I used, which I don't know yet. So I'm going to do one more stoichiometry from my limiting reactant, 0.00400 moles of lead 2. And 3 moles of lead 2 for every 2 moles of phosphate. If you're not sure where I found those, come back to your equation. 3 moles of lead 2 for every 2 moles of phosphate. And that means that I would use 0.0026666 repeating moles of phosphate ions. Okay? The excess then will be the starting moles, which were, I have to find them, I know them already, 0.00300 moles. So this would be my starting moles, 0.00300, minus my used moles, 0.0026666 repeating, which gives me 0.00, oh, it's a really small number, 0.003333 repeating moles of phosphate left. I have 3 significant figures. When I take that, now if I want molarity of that, molarity of my excess PO4 is going to be those moles divided by my new total volume again, because they're swimming in that bigger swimming pool of oh, you're going to hear Mr. Roke in the background, sorry, of 300 liters. And that gives me 0.0111, like so. Okay, excess remaining. Done. So this is tricky. We're going to practice this in class. Make sure you have your example with you to follow. Make sure that you have these steps written down and be ready with questions. I'll see you soon.